Hello, students. So this is the last part of chapter 11, and you guys have learned a lot so far. You've learned about the two different types of substitution reactions, so SN2 and SN1, also the elimination reactions, E1 and E2, and now we're just going to pull it all together. And sometimes it's hard to predict which one's going to occur. So I'm going to give you the tools in how to decide which mechanism is going to be operative, and then you could be able to predict the products. So let's just look. You guys have already learned all this. We're just doing a summary and just some synthesis and some practice. So predicting products, again, can be challenging just because sometimes they're competing with each other, the substitution and elimination reactions. So there are cases where you do get a mixture of product, but there's some cases where you actually exclusively have one mechanism occurring and you get mainly one type of product. So the goal is to predict and identify possible pathways, the possible products, and whether you have major or minor products. These are your main guidelines here. Number one, look at the reagent. This is going to give you a lot of information. Look at the substrate. Based on primary, secondary, tertiary, it'll also help give information in terms of what mechanism is going to occur. And then you can consider any different regiochemistry or stereochemistry from that. First, the function of the reagent. You need to ask yourself, is this a strong or weak nucleophile, or maybe is it a strong or weak base? So strong nucleophiles will favor SN2 reactions. Weak nucleophiles will favor SN1 reactions. If you have a strong base, then E2 elimination will occur more likely. But if you have a weak base, E1. Okay, so let's break it down to how do you know, is it a strong, weak nucleophile or base? Look at my chart. If you have a strong base or weak nucleophile, these guys fall under that category. So tert butoxide, DBU, DBN, which are shown here. Also sodium hydride. Hydride is a H-. It'll deprotonate and get another H to become H2 gas. These will favor E2, the elimination mechanism. If you have a strong base as well as a strong nucleophile, then you can have E2 or SN2. Look at my examples. Look at these and just categorize them in your head. Oh, these are small with O-, an actual minus charge off an O. Small guys, so they can get into that tight transition state and undergo SN2, but they're also strong bases, so they can do the E2 as well. Okay, the next category is weak base, strong nucleophile. So a weak base comes from a strong acid such as HCl, HBr, HI. So these anions, they're weak bases, but they're good nucleophiles because they're larger, they're more polarizable. This also applies to S- or SH. So in that case, you do have a substitution being favored, and it could be SN1 or SN2. When you have weak base and weak nucleophile, the only thing that's going to occur is E1 or SN1. And look at these guys. These are the neutral versions of what we had over here. So water, methanol, and ethanol. Okay, so this is something you want to just categorize in your head for yourself. Now we can map this against the substrate. Is your substrate primary, secondary, or tertiary? Let's break this down. If you have that strong base, such as DBU, DBN, terbutoxide, these guys are weak nucleophiles as well. So the only thing that's going to happen is E2. You'll get the elimination product. I don't care what your substrate is. Know that. Let's look at the other end, the weak base, weak nucleophile. So that's just water, ethanol, methanol. The only thing that will happen is if you have a tertiary substrate that can generate the tertiary carbocation, and then SN1 or E1 can occur with your weak base or weak nucleophile. The reason is these are weak, so you need a substrate to help you and generate that carbocation to get things going. If you have now, let's go to the second column, strong base, strong nucleophile, it depends. Remember, SN2 is favored for primary substrates, primary halides. So that will be dominant here. If you have a secondary tertiary, then the elimination E2 will be dominant. If you have a weak base, strong nucleophile, mainly you're going to get substitution. But if you have a tertiary halide, then the SN1 will dominate. Okay, now for consideration of the regiochemistry and stereochemistry. You need to look at the reagent and the substrate. You predict the reaction. Then you determine what type of product you're going to get. For example, maybe you have SN2, then you know that's concerted and it goes through inversion of stereochemistry. So that's your strategy. SN2, you definitely attack that alpha carbon. You get inversion of configuration. E2, that's an elimination. So you get an alkene product. The Zaitsev, more substituted, is favored. If a bulky base is used, however, then the Hoffman product is preferred. Stereochemistry, the trans is favored over the cis. And also, only alkenes that result from anti-periplanar arrangement and of the leaving group and beta hydrogen occur. SN1, you attack the alpha carbon as usual. Since SN1 goes through that free carbocation, it's that stepwise mechanism. The free carbocation, if there's an energetic reason to do so, it can undergo a rearrangement or such as a hydride shift or methyl shift to reveal, for example, a tertiary carbocation. That will happen. Stereochemistry, because you don't have that concerted mechanism from the backside exclusively in that trigonal bipyramidal transition state that you do for the SN2, this goes through the planar carbocation. So you do get a racemic mixture, but with a slight preference for inversion. E1 is elimination, but through a carbocation. Still, the more substituted Zaitsev product is formed and the trans isomer is preferred. Okay, let's practice. So you have this secondary alkyl chloride, and you have a small reagent, sodium methoxide, that I would categorize as a strong nucleophile and strong base. So pause and just write out what you think the product is. So the product that you'll get out is a mixture of elimination and substitution product. The reason is this is a very good nucleophile and base, and you have a secondary alkyl halide. So you'll get your elimination product, and this actually is going to be your major product. So that falls under the category of SN2 or E2. But because it's secondary, you get a little bit more elimination product out of that, and the Zaitsev trans product is favored. The other product that you will get out is the substitution. And since this is SN2, the substitution goes through that trigonal bipyramidal transition state, concerted, backside attack. So you get overall inversion of that configuration. So your O-ethyl will be opposite the chlorine. Okay, let's do two more. Pause and write the products here. For the first one, what I look at is, first I'm using DBN. This is a strong base but weak nucleophile. So E2 is going to occur. It doesn't matter what type of substrate, E2 is going to occur. Since there is only one type of beta hydrogen to eliminate, to deprotonate, then you're only going to get this single product, only one type of alkene. If you put the double bond here instead, that's the same compound, just rotate around this carbon-carbon bond. For B, we'll look at a couple things. We have ethanol, so it's not a ethoxide, so this is a weak base and weak nucleophile. So if you remember in the chart, what's going to occur there is possible SN1 or E1 when you have a tertiary alkyl halide. So this will, the iodide will leave, it's a good leaving group, and you reveal the tertiary carbocation. Then the ethanol can either add in and give you the substitution product, SN1 product, or you could deprotonate a hydrogen, and it's actually this hydrogen here, because that's preferred to give the more substituted Zaitsev product. So those two can occur. We're going to say it's about equal amounts. Okay, one other reagent I want to mention is cyanide. You guys have seen this once before, but cyanide, this is a good nucleophile. It's a moderate base. You'll mainly see it used as a nucleophile to add in and undergo a substitution reaction to give nitrile products. Another type of substrate I just want to remind you of are alcohols. We saw this in the formation of alkyl bromides in chapter 10. And basically, you can protonate the OH to make water a good leaving group, and then just substitute in with bromide. So the way that works is the lone pair adds the H, you kick out bromide, this creates water as a good leaving group. Then bromide comes in to undergo the substitution on this primary substrate, and you get your overall SN2 product, the alkyl bromide. Just to let you know, in protic solvents, the SN1 is favored. But since a primary carbocation is very unstable, the primary alcohol here is going to follow SN2 mechanism. However, if you have a secondary or tertiary alcohol, what will occur first is protonation of the alcohol. The water is a good leaving group, and you form a tertiary carbocation in this example. So that'll leave first, stepwise mechanism to give the free carbocation. So it undergoes this SN1 mechanism. Bromide then comes in, giving the tertiary bromide. Okay, 2 slides on just your overall synthesis strategies. This is first a primary halide that we're going to work with. Before I get into that though, I just want to really impress upon you the key to synthesis is just really synthesizing a variety of different types of organic compounds, some of them complex, but we want to do this in an efficient manner with cheap and readily available compounds. And you guys have learned so many reactions. You guys can do this. You guys have very powerful tools to synthesize a ton of different compounds. Look what we could do with a primary alkyl halide. We could do a substitution and install an OH to make an alcohol. An alcohol could also be reconverted back into an alkyl halide. If you react the halide with cyanide, you can generate a nitrile. If you want to use a strong base and weak nucleophile, you can generate an alkene. Look at this. What if you want to get an ether product? So COC. You can react with O-methyl or any alkoxide and generate the ether product. Reacting with SH- can generate thiol products. And look at this. An ester, how do you make that? You can see that if you could disconnect here and come in with an acetate, C double bond O-, that can be a nucleophile, kick out the bromide and generate your ester product. So very powerful methods to synthesize so many different types of organic compounds. If you had a tertiary halide, you can convert an alcohol sorry, if you have a tertiary alcohol, you can convert that to the corresponding alkyl halide. And then if you wanted to go the other direction, you could just add water in a solvolysis. This alkyl halide could also be deprotonated at a beta position and generate a Zaitsev alkene product. If you wanted the Hoffman product, you can treat with a bulky base and get this less substituted alkene. You could also convert your alcohol to those to the Zaitsev alkene as well. Okay, so you have a lot of different methods to synthesize products. So one of the key things in being successful in doing synthesis is just knowing these reactions and then just pull from that tool belt of yours. We'll go through a method of how to kind of deconstruct and work backwards and be able to use your reactions to synthesize products. Okay, we call this backwards method retrosynthetic analysis, and it's basically a way to make a map of how you're going to synthesize something. We work backwards from the desired product from readily available starting materials. So first of all, the one thing that you want to do is identify a bond that could be made using reactions you know. So if you wanted to make an ether, you could disconnect this near the oxygen, either here on the left or the right, because you know you can create an OC bond by taking an O- and adding into an alkyl halide. So let's disconnect here on the left. So that could bring you back, like I said, to an O-. In this case, we have 2 carbons, so that could be ethoxide. And let's make this an electrophile, so I just add a bromide here, or a bromine here. So these are 2 possible fragments. The way that you write an actual retrosynthetic approach is you show a kind of a dashed line, and then you do a large arrow, kind of 2 lines or a big arrow, going to basically deconstructing back to the 2 fragments. This is your retrosynthetic arrow. So this is just what we said, we're just showing this in this direction. And this is just rewriting it, but you also want to double check. You need to now go in the forward direction and make sure it makes sense. Okay, if I have this alkoxide and this bromide, then I can look to see if this is actually going to work. So if I take this strong, unhindered nucleophile, this is good for SN2, and I take this primary substrate here, this is good for SN2 as well, do this with a solvent such as DMSO, I can get my ether product. And let me just double check one thing here. So I did this the opposite direction, shoot. Okay, in my example, I actually did the disconnection here. And I'm going to show you another way in a second. So in this case, I made this the O- here. So this is one method. I'm going to show you a second one as well. So this is the disconnection I'm showing here. I apologize. So if you go back, this is one possible disconnection between a bromide and this alkoxide, the sodium ethoxide. This can work. I showed a second one here where we disconnect on the right side and we use this alkoxide and this bromide. So this also works. So there are 2 methods, and I did intend to show you 2. I apologize for just the way I did it. But again, after you do those disconnections, double check that that works. And it makes sense. Here you have this primary unhindered nucleophile, good for SN2, primary halide, good for SN2 as well. Okay, and then here I'm showing that original disconnection, the bromide, alkyl, the longer chain with the bromide, this also works, and reacting with the right piece of sodium ethoxide, DMSO, that will give you the exact same product. So both work, both would be correct answers. Why did I use DMSO? The reason, maybe you could think about it, the reason is that this is going to undergo an SN2 reaction. You've got a primary alkyl halide, a strong nucleophile, and aprotic solvents. Polar aprotic solvents are best for SN2. Okay, let's practice this one. You're going to form this ester. So pause this, write out how you're going to do it. Do a retrosynthetic analysis, do a dashed line or squiggly line to break up the molecule, write out the fragments you think should connect, and then rewrite an actual synthetic route. Okay, so my retrosynthesis, I disconnected here, similar to the other one where you have O minus and then you can envision an alkyl halide on this right side. I didn't disconnect on this side because we haven't talked about making esters from an O and then connecting at a carbonyl group. So this is the best disconnection for you. My retrosynthesis here, I'm using this type of big arrow. I'm going to get an acetate anion and as my nucleophile, and then ethyl iodide as my electrophile. You could have used ethyl bromide. I just changed it up. So that's my retrosynthesis. And then now I write the proposed synthesis in the forward direction. I would use sodium acetate as my reagent or substrate, however you want to look at it, and ethyl iodide. This will proceed through a SN2 mechanism because acetate's a good nucleophile and you're using a primary alkyl halide here. So I chose, again, a polar aprotic solvent. I just used DMF. That's another one. Acetonitrile is another one, just to change it up, and you will get your ester product. Okay, let's do another one. Provide the synthesis for this molecule shown. This is an ether product. So go ahead and pause and do a retrosynthesis and then do a proposed synthesis in the forward direction. Okay, so I disconnected here between the O and the tert-butyl group. So you can have this coming back to methanol and this a tert-butyl bromide shown here. So in the forward direction, I could have my bromohalide, I'm sorry, my alkyl bromide here, and I can undergo a solvolysis with methanol. So since this is a tertiary alkyl halide, this will want to undergo a solvolysis to give the carbocation, and the methanol can come in here and do its substitution. After proton exchange, you could get O-methyl, the desired product here. So this is going to go through an SN1 reaction. The reason is you have a weak nucleophile. I specifically chose this weak, so I wouldn't strongly get a ton of elimination product. You'll still get a little bit of elimination here, but a weak nucleophile, weak base will give you, with the tertiary alkyl halide, will give you substitution product, and admittedly, you will get some elimination, but you can separate those. Especially the polarities are very different. It would be an easy separation. And so it's a solvolysis because methanol is a solvent and the nucleophile in this case. Okay, this is where I'm going to end and just really practice. I'm going to post a practice worksheet, practice your synthesis. If you haven't really sorted out in your head how to do or distinguish between SN1, SN2, E1, E2, sit down, really solidify the mechanisms in your head because that really will help. It'll help with predicting what the products are, predicting the stereochemistry and regiochemistry. And then once those are really solidified for you, then really start applying them in synthesis problems. Okay,